Okay, sorry about the delayed start today. Well, I wanted to start with OpenGL programming from today, but I realized that I didn't cover one important topic. Like in other semesters, I had it covered by the first midterm, but for some reason we haven't done it in this semester yet. And it's quite important to understand those things before we move on to the programming aspect, because we'll be calling methods that need those things. These are stuff that you have covered in other courses mainly, but we'll just look at it from a different angle. The topic for today is called affine transformation, and the idea is that we need to we need to know the math background behind the translation, rotation, and scaling. Are these terms familiar to you? I think you have covered these things in coordinate geometry. For those of you who can't relate to these, let me just give you a brief reminder of what it is. So to start off with, let us imagine that we got a 2D coordinate system to make it simple. And this is the y-axis, and over here we got the x-axis. Alright, so for any point, let's say we got a point over here, and the coordinate for that point is given as, this is P1, let's say this is given as x1, y1. We want to know what if we need to move this point over, like say 1, 2, 3, 4, 5, 6 units to the right, and 2 units to the top, right? If that's what we want to do, 6 units over here on the x-axis and 2 units towards the y-axis, then what's going to be the new location of this point? Okay, that's what we are trying to find out over here. So let me just call this P, and the other one we'll call this P prime. So we'll have another point, P prime, given as x prime and y prime. I'll change the notation for those two as well. So we have xy at this location, and the new location is P prime, given by x prime and y prime. So we want to find out what's going to be the coordinates of the new location. Okay, so what we know so far is that our initial location is at 1, 2, 3, 4. It's actually at 4, 4, right? P is at 4, 4. So what's going to be the new location for P prime, or P rather? Ten, 6, right? So this is easy. We already know that this is 4 units to the right, and you want to travel 6 more units. So 6 plus 4 is 10. And if you go towards the y-axis, you already traveled 4 units, so 2 more units, that's 6. So this is going to be the new location. What we know here, let me write it down. This P point is given at 4, 4, and we already know that towards the x-axis we need to move by 6 units. Towards the y-axis we need to move by 2 units. So we want to find out what's P prime. And P prime is actually whatever you had for x plus dx, and whatever you had for y plus dy. Is this clear? So this is what we call translation. Okay, and if I bring up this blender, Let us just go with something a little bit simple. It's just a plane, all right? So this is just a plane, and let me also bring up the screencast keys. This is not going to be anything fancy. Still, you can see what I'm doing. So over here we got 4 points instead of just 1 point, right? And these points are given by this corner point is at 1, 1. This is at 1, minus 1, right? And you can look them up right over here. This one says 1, minus 1. This one is minus 1, 1. And this is again minus 1, 1. Alright, so if you select all these 4 vertices and you want to move this entire polygon 2 units to the right, what we can do, grab x2, and that's what it does. So it moves 2 units to the right. And this location was previously 1, 1. And now it should be 3, 1. This is going to be 3, 1. Because in moving towards the right, we didn't move the y-axis at all. It's only that the x coordinate would change. So our formula is pretty okay. And what you'd realize in coordinate geometry, we only maybe was worried about the points, but this face is made out of 4 points. So you can apply the same translation to all 4 points, and the whole thing will move towards that location. So previously, this point over here, this one was at minus 1, 1, right? Let me do it for you. So previously, before moving, well, I'd have to move it again. Grab x minus 2. So this was the location, right? So if you look at the coordinates, this one was at minus 1, 1. But when you move these things 2 units to the right, this one becomes 1, 1, right? So it moves only to the x-axis 1 units. And the same thing can be applied if you apply for any arbitrary translation we're grabbing. If we want to place it over here, we are actually measuring how much we're moving towards the x-axis and how much we're moving towards the y-axis. It can be a positive move or it can be a negative move. It doesn't really matter. It only matters whether we know the displacement in the x-axis, which is given by dx, and also the displacement in the y-axis, which is given by the dy. In coordinate geometry and SSA, HSC, you probably use these symbols HK, but they mean the same thing. How much you're moving towards the x and how much you're moving towards the y. Is this thing clear? Okay. So with this simple tool or this simple formula, P prime equal to P prime plus the displacement, we can simply write it down as we have this original location of this point P, and we want to move by a certain amount, which is given by D. So if you add those up, we get this new thing. Okay, and we can actually use a slightly different notation. You'll find out how this is going to be helpful. So this original location is given as 4, 4, right? And we can write it as a column vector or a single column matrix. This is a 2 by 1 matrix. It has 2 rows and 1 column. This is the x coordinate, which is 4, and this is the y coordinate, which is also 4 for this particular thing. And this is what we call this P point. Okay, and added to that, if you add the displacement vector, which is another column vector or a single row matrix, we are translating this towards the x-axis by 6 units over here and 2 units towards the y-axis. So the new location that you'd find is going to be another point, and the dimension for this matrix is going to be 10, 6, but the dimension is going to be 2, 1, right? 2 rows and 1 column. That's going to be the dimension. And we know how to add matrices, don't we? You go by component, you add them up, and you write it down. So first column, first row, first column, first row over here, 6 plus 4. That's 10, and over here is second row, first column, second row, first column, that's 6. So it's the same thing, it's just written in a different form. It's written as two matrices getting added. Is this thing clear? Okay, so this one is for translation, and we want to go for the other ones. Like I wrote in the previous page. Not here. We're going to study three things: translation, rotation, and scaling, and they all fall under affine transformation. You're transforming a given polygon to something else. But what you need to remember that while doing so, we are already keeping the points together. So over here, in this quadrilateral, when you move it to another point, say this is point 1, and this is point 2, and this is point 3, and well, let me write it down in the proper way. I mean, this was not proper numbering. So P1, P2, P3, and P4, we should go counterclockwise just to keep the angles right. So once we have that, you see that P1 is affine to P2 and also P4. By affine, I mean it's neighboring to P1 and P2. It maintains that affinity. P2, on the other hand, is a neighbor to P1 and P3. Okay, so when we translate this over to some other point, they still maintain that affinity. This P1 over here is still neighbor to P2 and also P4. And the same thing can be applied to any other thing. Like when you translate something over, let's say I got this wallet and I want to translate this over from here to this point in this 3D world, and it's not going to deform. It's not going to change its shape, so in a way that the vertices, they lose their affinity. Okay, and that's the reason we call them affine transformations. So you'd have to realize why they're called so. And over here, there are actually 4 different affine transformations that's usually covered in computer graphics. Translation, rotation, scaling, and the one that I didn't write over here is called shear. But I'm not going to cover that over here because, well, in this course we won't find much application for that. Although it itself is a quite important transformation. So we have only covered the first one from here, which is the easy translation stuff. Okay. So let me go for a scaling, and I want to set up the coordinate system just like I did before. And for scaling, let me show it over here first. Let us take the same cube, well, not the cube, the plane to start with. And this time around though, I'm going to change it a little bit. Okay, let's say we have a deformed quadrilateral, which was a square before, but right now it's not a square anymore. This point is at -1, 0. This is at 1, -1, and this is at 1, 1, and this is at -1, 1. We know the coordinates, right? Because this one is right at the center. This is 0, 0. The origin is right here. Okay? Now my question is, if I want to make this bigger or smaller, the operation that we perform is called scaling, right? In Blender, we could perform this as selecting this thing and then pressing S for scale and make it bigger or smaller. Okay. Let's say I want to make it twice as big, so I can write S2, and that makes it twice as big. Let me keep a copy of this. I'll duplicate this. S2. So we got the scaled version. And over here, Let me put it in a different color just so we can watch it better. So we'll have two materials. Okay, and just so we can see this better, I'd like to move it up a little bit so that you can see it this way. Now, this is the red one is the original quadrilateral, and the green one is the scaled version of it, right? So what we want to find out is that we have 4 vertices in the original one, and in the scaled one, obviously, we'd have 4 vertices. We want to know what's going to be the new coordinate. So if this is P1, this one was at, what was it? -1, 0, right? So we want to find out, if you scale it twice, what's going to be the coordinate of this one. Or for the same matter, how can you deal with the other ones as well? So as you can see, this is at 1, 1, and this one is at 1, 1.75, which is kind of strange. Okay, something went wrong. Let me delete this one and redo this. I know why it happened in that way, because we have a median as a pivot point. I don't want to do that. So again, I'm selecting all of that, Shift D to duplicate, and this time around, instead of going with the median point as pivot, we are going to use the 3D cursor. We have changed the pivot in other applications. I think we did it for the PichiPoi human meter rig. I showed you how you can change the pivot point so that you can move from the shoulder or the elbow joint and such and such. So I'm going to do the same thing, but this time around it's going to look different. Scale twice. So I'm going to apply it the green material and the Z coordinate. I want to set it down to 0. So yeah, it looks a little bit different, right? So this point is originally at 1, 1, and after scaling it becomes 2, 2. This point is at 1, -1 originally. Let me label them so it's easier to talk about them. This is P1, this is P2, P3, and P4. We got 4 points. What we want to find out is how are they transformed. So from P1 to P1 prime, what's the formula? And then from P4, how do you find P4 prime? Or from P3, how do you find P3 prime? And finally, the last one, P2 prime. So at P2, what you see is that it was originally at 1, -1, and at P2 prime, this is at 2, -2. This one, P1, is at -1, 0, and this is at -2, 0. So can you guys see the pattern, or can you recall from your coordinate geometry class what's the formula for scaling? What we know over here is that we want to scale it to be twice as big on both the axes. So if we want, you can make it different. So for example, if you select these 4 points and scale it only on the x-axis, this is possible. The scaling factor on the y-axis is 1. We're not scaling at all. So if you say is 1, that really doesn't scale anything because that's the one scaling factor. If you scale it twice, it's going to make it twice as big. If you scale it 4 times, yeah, not like that. It's going to make it 4 times bigger. That's the idea. But if you want to make it smaller, you say like is 0.5, it makes it half as big. Okay, so you can go with any number greater than 1 or less than 1 if you want to change the shape of it. And you can also do it for different axes. Okay, so what I'm really looking for is a formula that lets us calculate what it really is. You're given any point over here. Let's say this is my point P, given by two coordinates x and y, and I want to scale it. This is at 4, 3, right? Originally this is at 4, 3, remember that? And what I'm telling you that I want to scale it on the x-axis by 3 units and on the y-axis by 2 units. So I want to find out what's going to be the P prime given this Sx and Sy. Any idea? Let me write it down. This is at 4, 3, and what's going to be this 3, 2. Okay. What's that? 12, 6. 12, 6 is the correct answer, yes. When you scale, and we can show this that this is going to be that, let us put this point at 4, 3. Okay, so we'll track this one. This is at 4, 3, and we want to scale the whole thing, okay, by 3 units to the right and 2 units to the top. So scale x by 3 units and also sy 2 units. Okay, the coordinate that I can read from here is 12, 6. So what he said is perfectly okay. I mean, that's the formula. But you need to realize what happens over here. This is what happens. You find the new coordinate by multiplying s by sx and y by sy. Okay, that's what you do. Scaling is a multiplying thing. You multiply the coordinates by the scaling factor. And scaling factor by 1, it means that you don't change anything, because if you multiply anything by 1, nothing changes. And for translation, if you don't want to move that object, if you want to keep it there, your distance, the dx and dy, they should both be 0, because if you add 0 to anything, it doesn't change the location or the values. So over here we have 4, 3, and now we are going to go to 4 units and 4 more units. That's 12, and this is 3, and this is 3 more. So this is going to be the new location of P prime, which is going to be x prime and y prime. Okay, so you go from here to there. That's a scaling thing. And we are just showing it for one particular vertex, but as you can see that it can be applied for the whole thing. Whatever object you have, when you scale that, you're actually changing all these vertices at the same time, so the whole thing gets scaled. So let me show you in a different layer. If you have a monkey face, the Susan monkey, just like this, it has a lot of polygons. So when we are scaling this thing, we're actually changing the coordinates for each and every polygon. All these vertices, they change. Okay, that's the idea. And you can also scale in different axes, like you can make it wide, or you can also make it tall. Actually, sz rather. Okay, so in that way we can have different scaling factors for different axes. Now, one interesting thing you'd find out is that if you look at this thing, we wrote this in matrix notation that P prime can be written as P plus D. My question is, can we write it down in matrix form for this one as well? Can we do this? No? Did you guys get the question? What I'm asking for? Say over here, we got a point, and the point is given as 4, 3. Alright, this is the original point, and we know how much we want to scale. This is 3, 2. Okay, can you write it down as a matrix operation, like either you add something or you multiply something to get the end result, and the end result, let me write this down again. The end result is actually 12, 6. So what I'm asking for is what goes in over here, or is it at all possible? And this is the scaling matrix. So instead of that question mark, can we put a multiplication right there? Because adding this thing simply doesn't help, because if you add them, you get 4 plus 3 and 3 plus 2. They don't add up to the result that we're looking for, right? So how do you do this? Yes, because you got a 2 by 1 matrix over here, and you got another 2 by 1 matrix. You can't simply multiply them. Okay. And for those of you who don't remember, matrix multiplication was defined in a way that the column number for the first matrix has to match with the row number of the second matrix. And that simply doesn't happen over here, because we have 1 over here and 2 on this side. So they don't match. So simply, multiplication is not an option, and addition doesn't really help. Is this clear? So when you realize that, I mean, you'd have to understand the solution as well, that addition cannot be a solution to this problem, and so multiplication doesn't even help. But this is essentially multiplication, as you can see right over here. So somehow we need to multiply this. The solution is not that difficult either. You just write down, what's that, 3 and 2. You just write down 3 and 2 like this. And is that going to help? So if you have a matrix multiplication written in this format, this is actually matrix multiplication. What's going to happen? In matrix multiplication, we fix the row for the first matrix and the column for the second matrix. So you're multiplying in this way, and whatever values you get in multiplication, you add them up for the result. So 4 times 3 is 12. Add it to that. No, I wrote it wrong. I wrote this thing totally wrong. This thing is not going to work because of the same problem. We got a 2 by 1 matrix over here, and over here we got a 2 by 2 matrix. So yeah, it doesn't work, and that's why I'm failing. Over here we got 1, and over here we got 2, so this doesn't work. We can't multiply it this way. But that's not an issue really. We'll improvise again. What if we write it down on this side? The point itself, we write it down over here. So this time around, if you pick the first row from the first matrix and the column from the second matrix, what do we get? 3 times 4 is 12, and 0 times 3 is 0. So we got 12. So we get the first part, right? And then for the For the second row and this column, we get 0 times 4, which is 0, and 2 times 3 is 6, so we got this number. So do you understand how we can write it in matrix form? Okay. So the scaling matrix need to be put first, then after that you put the point, and you can multiply them to get the new location of this point P prime right over here. So you just do the multiplication like this. But in the previous one, we wrote it in addition format. Just to keep it consistent, you can actually move this point P over here. It's no big deal. I don't want to do this. So I can also put it over here, right? And they would mean the same thing. It doesn't make any difference. So far we have only covered translation and scaling, but in the first slide you see that there is one more operation left, which is called rotation. So we need to figure out how we can do the rotation and write down the mathematical formulation for that. Okay. Before we get there though, let me give you a brief example or idea of what we are trying to achieve over here. For animation or for any sort of modeling also, we need a lot of things. For example, let's say we got a cube like this. I want to change the shape of it. So let's say we get a stick-like cube, right? And we want to move it towards the x-axis by 3 units first. And after we move that, then we want to scale it twice. All right, so this is going to happen. Okay. First of all, we moved it on the x-axis 3 units. Then we scaled it twice. Make it twice as big, and this is the end result. Now my question is it going to be the same if you scale it twice here and then move it to the x-axis by 3 units? Okay, let me leave a copy of this. Let me duplicate this. So first of all, we moved it to the x-axis, grab x 3 units. Okay, so we moved it there, and after we moved it, we scaled it is 2, and this is the end result. What I'm doing here, let's say this is the other copy, and I'm duplicating this. I want to scale this first, is 2, and then move it, grab x 3 units. They're not the same, right? So the order of the operation matters, and these operations can be changed one after another to do some particular animation. So if you have a keyframe animation, you can say that I have a lot of things. I want to move this thing, I want to rotate it, I want to make it bigger. So you can have a lot of operations going on one after the other to come up with some sort of animation, and something that you can relate to, which is also going to be a good example. Let me set this up. Let's say we want to design our solar system. We want to animate that, we want to model that. Can we do this? The solar system has the sun right at the center. All right, let's imagine that this is the sun. Okay, and we have a lot of planets that are revolving around this thing in their orbit. And the orbits are not circular, they're elliptical, but for simplicity, I'll just say that they're all circular orbits for this thing. So what we want to do here is we want to create another copy. Let's say I'm duplicating this, and we want to make another planet. So grab and move it to the x-axis, let's say, by say 3 units or whatever. So I move it over here and I want to make it smaller. Okay, but I mean that's probably not the way. I mean, if it's the Earth, let me make it. Yeah, let's imagine this is the Earth right at the center, and now we want to move it, say 4 units to the right. Okay, this is not the right scale, definitely not. Sun is a lot more bigger than this one. Okay, but this will give you an idea. So let's imagine that this is our Earth. So what's going to happen? This thing is going to rotate around the Sun like this. What are the operations that we had to do on this particular sphere? We had to scale it down first by a certain amount. So we have to know the radius of the Sun first. Let's say this is 1 unit for Sun. And compared to that, if you know the radius of the Earth, you can make it smaller. Take the same sphere, make it smaller. Then you need to translate that so that you have the radius of the orbit. And after you move it over, when you know the radius of the orbit, then you can start rotating this around the Sun. Is this clear? So right now this is at, say, rotation 0 degree, and after some point it would be at rotation 45 degree right over here, or rotation 90 degree. Goes like this. Can we do a keyframe animation for this just so you can follow? Yes, no? So first of all, I want to save the rotation over here. This is 0, and let's say after 80 frames the rotation is going to be 90. So I'm going to insert rotation over here, and going from this frame to another, what? Something's not right. Oh, I haven't applied the scale and anything else. Rotation and scale, and also the location, I guess. Now it's working. So previously, the thing that was wrong was that I didn't apply the scaling and the rotation, so it wasn't calculating properly. So right now you see that it's orbiting, right? But maybe I want it back over here. So instead of saying that rotation is 35 degrees, I'd say this is 359 degrees. That puts it over there. Actually, I can also try with 360 and try to insert the rotation and see if we change anything. Yeah, it does. Okay. So if you want to do this animation, this is at 80, so I'd stop at frame number 79, just so we have a repetition. And now we can let it play, and we have a Sun right in the middle, and then this whole thing is rotating around like that. There is a bit of pause because the way this is calculated, the keyframes, it's done in a slightly different way. It's not really linear. There is a slowdown right at the start and slowdown right at the end. So we can change that, but that's not the point right now. So you can imagine that this thing is rotating in a constant speed, which is it isn't, but you can always assume that it is. Now this is just a simple example of multiple operations going on one after another. So we scaled it first, we translated it, and we also rotated that. So if you can imagine that this sphere right here, it has a lot of polygons. All those polygons, the faces, they are joined together to form this sphere. And to make each of these polygons, you'd have to know the vertices for each of them, right? So the question is, if you know the time Like if I tell you at time t equal to 30, what's going to be the coordinate of a particular point on any of these polygons? Can you trace that? So just to make this clear, let me pause that, and let's say I go to frame number 30, and right over here, see there are a whole bunch of polygons, and I select a face over here. Let's say I selected this face, and if I want to ask what's going to be the location of this point or this point or this one or this one, you should be able to tell, because when we render this animation, we are actually pinpointing each and every vertices. We are drawing them out in our scene. So you need to be able to calculate the location of each and every item, because this is constantly changing. As you can see, this point or this polygon is actually traveling in time with different coordinate values. Okay. So we need to set it up in a way that we can calculate these things based on some parameters, and the parameters can be the scaling factor, it can also be the displacement factor, how much we moved, and also the rotation factor. And they can be chained one after another to form something like this. And to make this matter more complicated, or at least more interesting also, let's say we got a sun, we got this earth, we can also have a moon, right? That's orbiting around this thing. How do we do that? Yeah, you just make another copy of this, Shift D to duplicate, right? And then the moon needs to be a lot smaller than the earth itself. I'm not going for a particular scaling or realistic value, but let me just make it half as big. So that's the moon. Okay, but it went over there because I scaled it based on the pivot. Let me change the pivot point. So the pivot point is going to be this one. Shift S cursor to selected. Okay, I've changed my 3D cursor, or have I? This is not the selected one. Okay, I see. Where am I at? 1, 2, 3, 4. All right. So the 3D cursor, where is that? I want to place the 3D cursor right here, and I can change it there. So Shift D, I want to make a duplicate copy, is 0.5, which is going to be smaller than that. And then I can move it over to the x-axis, grab x, say 1 unit over here. So this is the setup, right? Looking from the front view, we got this thing animated. Okay, this is the sun, this is the earth, and this is the moon. So in a realistic scenario though, like this thing should be orbiting around the earth itself, so you want to move it like that. Okay, while the earth is moving, this one shouldn't be here, it should be orbiting around the earth itself. We can do this animation in Blender, no problem with that. But to realize how you can do that in mathematics, because in Blender they have also implemented all these things, translate, rotate, and scale. They have implemented so that we can do all these animations. So if you want to write a computer program, you should be able to write it by yourself or use some library where these things are implemented. The scale function, the rotate function, and the translate thing. Okay, all these things are implemented, and we need to do it in matrix form. I'll also give you a reason why we want to do that. So just a bit. I didn't want to close that.